Longest common subsequence. What's the longest hidden pattern two-string share? Longest common subsequence is a pattern mastery 100 staple and a classic in dynamic programming, beloved by Google, Facebook, and top tech interviewers. This problem tests your ability to break down problems into overlapping sub-problems and optimize with DP, a must-have skill for tough interviews and real-world software challenges. Let's break it down. Given two strings, return the length of their longest subsequence, not substring, that appears in both. A subsequence can skip letters, but the order must stay the same. Now, let's assess. Brute force would try all possible subsequences, exponential time. Dynamic programming is the standard and optimal solution here. By building a DP table where each cell dpij represents the length of the LCS for text 1, I, and text 2, j, we can reuse previous results and solve the problem in OM times n, time and space. Here's the plan. Create a DP table of size, len text 1 plus 1, times, len text 2 plus 1, filled with zeros. For each index I in text 1 and j in text 2. If text 1i minus 1 is equal to text 2j minus 1, then set dpij to dpi minus 1j minus 1 plus 1. Else, set dpij to max dpi minus 1j and dpij minus 1. The answer is in dp minus 1 minus 1. Solution 1. Recursion with memoization time complexity. OMN. We begin by creating a class named solution. Think of it like a toolbox that will hold our function. This line defines our main function. Its job: find the longest common subsequence, LCS, between two strings, the longest sequence of characters that appear in the same order in both strings. We measure the lengths of both strings and store them as m and n. This helps us set boundaries for our recursion. Time complexity note: getting lengths is O1 for Python strings. We set up a dictionary called Memo. This serves as our memory, a place where we store answers we've already computed so we don't repeat expensive work. This memoization keeps our overall complexity at OM times n, instead of exponential. Here we define a helper function called DFS, short for depth first search. This function will recursively explore the two strings starting from positions I and j. This checks whether we've reached the end of either string. If we run out of characters, there can't be any more matching subsequences. In that case, we return 0, meaning no characters left to match. This line checks our memo dictionary to see if we've already solved the LCS problem starting at positions I, j. If we have, no need to redo the work, we simply reuse the stored answer. And if we did store it earlier, we return that value immediately. This saves us a huge amount of time, avoiding repeated recursive calls. Now we check if the current characters match. If the characters at positions I and j are the same, that means this character is part of the LCS. If the characters match, we record in Memo that the LCS length at I, j, is 1 plus whatever we find when moving both pointers forward. It's like saying, we found a matching character, now keep searching the rest. If the characters don't match, we have to try both options. Option 1, move forward in the first string. Option 2, move forward in the second string. Here we choose whichever option gives a longer subsequence. We compare the results of two recursive calls and store the best result in Memo. This also ensures we don't recompute the same overlaps again. Before finishing this recursive call, we return the value we just stored. This ensures every step bubbles its result upward until we reach the final answer. Finally, we start the recursion from the beginning of both strings, positions 0 and 0. The result of that call is the full length of the longest common subsequence. Final wrap-up. And that's how this algorithm works. It first sets up the string lengths and a memo to avoid repeating work, then uses a recursive search to explore matches and mismatches while storing results for speed. Efficient, simple, and elegant. Test case check. Longest common subsequence, recursion plus memo. Let's test our function using this input. Text 1 equals ABAT and text 2 equals ACE. These strings represent two sequences, and our goal is to find the longest ordered subsequence that appears in both of them. Here's why the solution works. Our recursive function compares characters at positions I, j. If the characters match, we include that character and move diagonally forward. If they don't match, we explore both possibilities, skipping a character from text 1 or from text 2, and take the better result. And that's exactly what our program outputs. 3. The result matches the expected value, confirming that the memoized recursion is functioning correctly. Wrap up. So, our implementation is correct. The algorithm successfully computes the longest common subsequence using recursion with memoization, efficient and accurate. Solution 2. Bottom-up DP table time complexity. OMN. We begin by defining a class called solution. Think of it as the container that holds our optimized LCS method. This defines our main function. Its job: compute the longest common subsequence between text1 and text2. We measure the lengths of both strings and store them as m and n. This helps us build a DP table of the right size. This step is constant time, O1. We create a 2D grid called DP, filled with zeros. The table has m+1 rows and n+1 columns. We start looping backward through text1, from the last character toward the first. This ensures the cells we depend on, the ones below and to the right, are already filled. Inside the first loop, we loop backward through text2 as well. So we fill the DP table from bottom right to top left. This ensures our subproblems are solved before we need them. We check whether the characters at positions I and j match. If they do match, this character contributes to the LCS. When the characters match, we add 1 to the LCS length found in the diagonal cell, DPI plus 1 j plus 1. That diagonal cell represents the result of comparing the rest of the strings. So this is like saying, these two characters match, count them, then continue checking the rest. If the characters don't match, we have to choose the best option. We look at two possibilities. Skip a character from text1 DPI plus 1j. Skip a character from text2 DPIJ plus 1. Whichever gives the longer subsequence is the correct value for DPIJ. This comparison is constant time, O1. But it happens inside two nested loops, resulting in an overall complexity of OM times n. Finally, we return DP00, the cell representing the LCS length of both full strings starting at index 0. That's our final answer. Final wrap-up. And that's how this algorithm works. It first sets up a DP table for storing the answers to all smaller subproblems, then fills that table bottom-up by comparing characters and building the answers step by step. Efficient, simple, and elegant. Test case check, bottom-up dynamic programming, LCS. Let's test our function using this input. Text1 equals ABAT and text2 equals ACE. These two strings represent sequences of characters, and we want to find the longest subsequence that appears in both strings in the same order. Here's why the solution works. We fill a 2D DP table starting from the bottom right corner, working our way up to DP00. At each position, I, j. If the characters match, we take 1 plus the diagonal value. If they don't, we take the maximum of skipping a character from either string. And that's exactly what our program outputs. 3. This confirms that the bottom-up DP logic is functioning correctly and matches the expected value. Wrap-up. So, our implementation is correct. The algorithm successfully computes the longest common subsequence using a complete DP table, efficient, accurate, and reliable. Longest common subsequence. Let's do a recap. We started by defining the goal. Find the longest sequence of characters that appear in both strings in order, though not necessarily contiguously. It's all about preserving order while skipping unnecessary characters. That's what makes it a subsequence, not a substring. Assess recap. We discussed how brute force would explore every possible combination. Far too slow. Instead, we chose a dynamic programming approach that builds up results from smaller subproblems. By reusing what we've already computed, we reduced an exponential problem down to efficient OM times n time. Structure recap. Our logical plan was to create a DP grid where each cell represents the LCS length for prefixes of the two strings. If the characters match, we extend the sequence. If not, we carry over the best length found so far. The final answer rests in the last cell, simple and elegant. Implement recap. We implemented the logic cleanly and ran it through LeetCode. The code executed without any issues, efficiently computing the correct subsequence length. Check recap. After running our test cases, we confirmed that the solution produced the right results and passed all validations, a solid confirmation that our DP structure worked perfectly. Closing insight. The key takeaway? Dynamic programming isn't just about memorizing patterns, it's about recognizing overlapping subproblems and using structure to turn complexity into clarity. Master this mindset, and you'll start seeing DP problems as puzzles that naturally fit together.